Hello, my name is Sarah Jordan. I'm a professor at the School of Advanced International Studies at the Johns Hopkins University. Today I'm going to be presenting on a paper that was published in Nature Climate Change that I co-authored with Dr. Kavita Surana at the University of Maryland on the climate mitigation opportunity behind global power transmission and distribution. Power generation is the largest single contributor to greenhouse gas emissions. It reached about 13 gigatons, or 38% of total energy-related CO2 emissions in 2018. These emissions take root not only in the power generation mix, but also in the vast infrastructure that can result in substantial inefficiencies. This comes from everything from power generation to the full grid, which has many places where power can be lost. This presentation will focus specifically on the inefficient transmission and distribution, or T&D infrastructure, that can result in reduced power grid efficiency and that can thus increase the total sectoral greenhouse gas emissions. Some examples include technical issues, losses, for example, from resistance in wires, pilferage, poor planning, and management. While recent research discovered that T&D losses can have a substantial influence on life cycle greenhouse gas emissions associated with electricity generation from liquefied natural gas export globally, it was only really completed for a small subset of countries. We had the opportunity in this research to look at a larger sample, 142 countries, and found that these emissions, which are often overlooked, can amount to near 1 billion metric tons of carbon dioxide equivalents per year. This presentation will take you on our journey of quantifying the mitigation potential associated with reducing these T&D losses. In order to meet this goal, we leverage a tool called Life Cycle Assessment, or LCA, which quantifies the environmental burdens of products and processes from materials extraction through waste management. It's also called a cradle-to-grave approach. The research that led to our question focused specifically on what are the life cycle greenhouse gas implications of increasing the export of liquefied natural gas, specifically from British Columbia. It turns out that any potential for environmental benefit depends on the importing nation's electricity generation mix, for example, if it's higher carbon. And what we found was that not all infrastructure is well characterized in life cycle assessment of electricity generation, particularly when looking internationally. And the transmission and distribution losses, as well as power plant efficiencies, were the two areas of infrastructure that we decided to examine further. But we quickly found it was more complicated than that. In work that was first authored by a postdoctoral fellow who is formerly with my group, Dr. Kasumu, we found that the infrastructure effects can actually be quite substantial. We found that while previous studies applied generic country-level emissions factors, for example, and did not examine the infrastructure effects, these effects can actually matter quite a bit for the life cycle results. These two panels show the life cycle greenhouse gas emissions in grams of CO2 equivalent per kilowatt hour delivered from liquefied natural gas that was exported from British Columbia to a number of different markets. The right-hand panel shows that natural gas burned in the United States without liquefied natural gas export at high efficiencies can be quite substantially lower than, for example, the natural gas that's exported and combusted in areas with much lower efficiencies and higher transmission and distribution losses like India. Dr. Surana and I decided to examine these in a much larger global context. How much electricity is actually lost in transmission and distribution? And how much can these losses contribute to emissions? T&D infrastructure can suffer from different types of inefficiencies. For example, losses can be technical or non-technical. Technical can be from, for example, physical limits, losses from resistance, aging infrastructure, grid operation, and maintenance. Whereas non-technical losses are those that would result from pilferage and stealing, fraud, or inefficient metering and billing. In our analysis, we consider T&D losses the percentage of generated electricity that is lost between the source of supply and distribution to the customer. Power plants thus are required to generate more than 1 kilowatt hour of electricity to deliver 1 kilowatt hour to a customer. We refer to this as compensatory generation, and we refer to the resulting emissions as compensatory emissions. Dr. Serrana and I sought not just to understand what these compensatory emissions might look like, but we also looked to understand what the overall emissions outcomes of reducing these losses meant for mitigation potential. At the 21st Conference of Parties held by the United Nations, a historic agreement was made, the Paris Agreement. As part of this agreement, all countries would submit nationally determined contributions which would outline how they would all make efforts towards reducing emissions. We became interested in whether or not these transmission and distribution losses have actually been examined in the nationally determined contributions. We examined 160 of the countries that submitted NDCs to the UNFCCC, and we found that 32 of these countries mentioned grid efficiency or T&D losses. 110 mentioned renewables. Life cycle assessment, or LCA, is a quantitative tool that examines the environmental burdens of products and processes from materials extraction through waste disposal, or cradle to grave. LCAs are known to be challenged with varying results, and that's because there are a lot of decisions in these analyses around what are the system's boundaries and input assumptions. Our analysis leverages a recent series of studies by the National Renewable Energy Laboratory called the Harmonization Studies. These studies entail systematic reviews of estimates of life cycle greenhouse gas emissions from different electricity generation technologies from 1970 through to 2010. Harmonization involves adjusting the estimates within the life cycle models so that more consistent and more comparable results can be obtained across studies. In these studies, transmission and distribution losses were omitted in the harmonization process. The overall goal of harmonization is to reduce the variability across studies and to clarify what the central tendency of life cycle greenhouse gas emissions are for different electricity generation technologies. In the present study, we asked the question, how much do T&D losses matter? In order to answer this question, we have to expand our system boundaries. In Figure A on the left, you'll see that we have system boundaries that delineate a life cycle assessment that would result in the emissions per unit electricity generated. This means that the system boundaries only go up to where the electricity generated from the power plant goes towards the transmission and distribution and deliveries to customers, but does not include it. What we examine in this study is the right-hand figure, where you see it's the emissions per unit electricity delivered. So this means that we actually include the transmission and distribution losses, that is the delivery to consumers. This figure shows an illustrative systems boundaries for the LCA in this study. It's illustrative in that it can be adapted for each of the countries that we examine. For each of the 142 countries that we analyzed, we looked at the grid mixes for each of them. Similar to the electricity generation mixes, we also collected information specific to each country about the efficiencies of the generation as well as the T&D losses. We used NREL's comprehensive review to quantify a distribution for each type of generation. Applying the grid mixes, we then determined the life cycle emission. For each country, we adjusted these results to represent the average power plant efficiencies from that specific country. To account for uncertainty in all of the inputs, we then ran a Monte Carlo simulation. Running 10,000 iterations sampling from the input distribution, we obtained a distribution for the possible outcomes for each country. Ultimately, what this provided us with was estimates for the potential compensatory generation and for reducing emissions from T&D losses in 142 countries. We found that these compensatory emissions result in near 1 billion tons of carbon dioxide equivalents a year. We then examined how many emissions can be reduced if these transmission and distribution losses are brought to OECD levels or lower. It turns out about half of these emissions can be reduced. The top figure shows the potential reductions in technical losses only. The bottom figure shows the case where non-technical losses are also included. For the former, we found that our average estimate indicates 410 million tons of CO2 equivalents per year can be reduced, whereas for the latter, for aggregate losses, our average estimate was 544 million tons of CO2 equivalent per year, with a maximum of 885. For each of the 142 countries in our analysis, we calculated the reduction in both technical losses and also aggregate losses, which account for the non-technical losses. In this slide, you will see the results for the reductions on emissions factors and also total emissions reductions over a year. We include emissions factors, which are the two top figures, to capture the fact that there are some countries which may have larger total emissions, but at the same time, the relative emissions intensity is low, such as the United States. Note the variability across countries, but also areas where mitigation potential is very high. For example, the emissions reductions potential in both China and India. A closer look at China reveals a similar result to the United States, where the emissions reductions as accounted for in the emissions factors do not appear very large. However, the aggregate emissions or the total emissions reductions in megaton CO2 equivalent per year are much higher due to the fact that these countries generate a lot of electricity. The electricity generation mixes in all of these countries, however, continue to evolve, which brings forward the question of how do reductions in transmission and distribution losses affect emissions over time? In order to explore this question, we looked at how much these losses might play into emissions reductions over 3 International Energy Agencies scenarios from the World Energy Outlook. We looked at the current policy scenarios where only policies and measures that are legislated as of mid-2017 are considered. We looked at the new policy scenarios, which includes policies in place and the likely effects of announced policies, including nationally determined contributions in the Paris Agreement, but also the Sustainable Development scenario where the Paris goals are met. For the Sustainable Development scenario, not as many emissions reductions can be seen, however, the grid is cleaner. For cases with less optimistic grid decarbonization, the potential for reducing emissions can extend above 1 billion tons of carbon dioxide equivalents a year. So what are the solutions? The solutions clearly require local considerations. Potential solutions for reducing technical losses might include improving transmission efficiency, for example, replacing inefficient wires and equipment, or improving distribution efficiency, for example, better load management, or adding more distributed resources, thereby reducing the transport distances. Non-technical losses are tricky. Potential solutions might include tamper-proof meters, managerial methods such as inspection and monitoring, and restructuring power systems ownership and regulation. In conclusion, by addressing these losses, not only are greenhouse gas emissions reduced, but lower carbon investments are protected from grid inefficiencies. It's very important, however, to think about the specific requirements of a country, the state of its infrastructure, and the structure and ownership of its power sector. We want to reinforce the importance of collaboration in determining regional and local solutions. This way, we can account for specific characteristics of space, time, power generation, but also determine the most effective and sustainable local infrastructure solutions. Thank you very much for your time and attention. Please do feel free to reach out to either of us if you have any questions. All videos shown in this presentation were downloaded from pexels.com.